Hello again. In our last video, we introduced three types of symmetry. We introduced the y-axis symmetry, x-axis symmetry, and origin symmetry. Now we're going to determine symmetry algebraically instead of relying on a picture. We will use the equation itself. So we're going to test for symmetry with respect to the y-axis, x-axis, and origin. So the tests for symmetry are as follows. Y-axis, we replace x with negative x. The x-axis of symmetry, we replace y with negative y for the x-axis. And then for the origin, we replace both. So again, when you're testing symmetry, if you're told to test symmetry with respect to the y-axis, then you want to replace x with negative x. You want to test symmetry with respect of the x-axis, you replace y with negative y. If you want to test symmetry with respect to the origin, then you replace both. You replace x with negative x and y with negative y. Okay. So again, that looks like negative x, y from xy to negative xy. Then from x, I keep doing that. Xy to x negative y, and then x comma y to negative x comma negative y. Okay, so again, replace x with negative x, replace y with negative y, and then replace both x and y with negative x and negative y. So the basic question is this: after making the substitution, do we get the original equation back? That's the question. After making the substitution, do we get the original equation back? If the equation remains unchanged, then the graph has that type of symmetry. So let's begin with an example. So the first example I want to look at is example 1. And we're going to determine whether the graph of y equals x squared plus 4 has y-axis symmetry. So the first example I want to look at is determine whether the graph of y equals x squared plus 4 has x-axis of symmetry. So for y-axis of symmetry, let me see, determine whether the graph of y equals x squared plus 4 has y-axis of symmetry. So for y-axis of symmetry, what do we need to do? For y-axis of symmetry, we need to replace x with negative x. Okay, so in doing that, we're going to take the equation y equals x squared plus 4. And again, we're going to change the positive x to a negative x. So again, that looks like this. Y equals negative x squared plus 4, because we want to determine whether whether this equation has y-axis of symmetry. So in order to do that, again, we replace x with negative x. Now, negative x squared is the same as negative x times negative x. Negative x times negative, or a negative times a negative, is going to give you a positive. So negative x squared is x squared. Negative x squared is x squared. So if we do this, we end up with y equals x squared plus 4. So notice the equation started here. It started here and it ended here. So the original equation ended up being the ended equation, or the final equation. And so this is exactly why we can understand that this equation has y-axis symmetry. So this is exactly the original equation that we started with from the first place. So therefore, the graph is symmetric with respect to the y-axis. Okay, so we just determined that. So if you encounter a problem like this, all you have to do, remember, is replace the negative, or excuse me, replace the x with the negative x, and then compute it. And then if you end up with the original equation, that is how you determine whether or not that equation is symmetrical with respect to the question at hand. A next example. This is example 2. Let's determine whether another graph is symmetrical with respect to another axis. So we're going to determine whether x equals y squared minus 1 has x-axis symmetry. For x-axis symmetry, as stated earlier, for x-axis symmetry, we need to replace y with negative y. So again, a helpful way to do this is to write this down. We're looking for this. We want to tend to change our y. Okay. So in doing that, we want to write our equation, which is x equals y squared minus 1. We're going to replace the negative, or the positive y, with a negative y minus 1. And again, negative y squared is negative y times negative y. Negative y times negative y is going to give you a positive y. So again, we obtained the original equation that we started with. Therefore, the answer is yes, x-axis of symmetry. Okay. Example number 3. Determine whether y equals x cubed has origin symmetry. Determine whether y equals x cubed has origin symmetry. For origin symmetry, remember we take our ordered pair. That ordered pair tends to negative x, negative y. So for the origin symmetry, we replace x and y with their opposites. Now we're going to write our equation, y equals x cubed. Substituting these values, we have negative y equals negative x cubed. So again, we have a cube root over here. So this negative x cubed is the same as negative x, negative x, negative x cubed. So we have three negatives. We know negative times a negative is a positive, and we know that a negative times a positive times a negative is going to give us a negative. So negative parentheses negative x cubed is negative x to the cube root. So since negative x cubed equals negative x to the third, the final result would be negative y equals negative x cubed. Now notice this. We're not quite finished yet, okay? So we got to be careful here. We get negative y equals negative x cubed. So what we have to do is multiply both sides by negative 1 to get rid of this negative here. So multiplying both sides by negative 1. When you multiply both sides by negative 1, I'm just going to put a multiply both sides by negative 1 here. When we do that, we end up with a positive y. And again, negative times a negative is going to give you a positive. So we started here, we ended here, and we obtained the original equation. Therefore, the answer is we do have origin symmetry. So notice that this example required an extra algebraic step. So do not stop too early and assume that this was the final answer. The transformed equation may need to be simplified before you noticed whether it matched the original equation. So when you get to steps like this, make sure you double check and see if it can be simplified before moving on. Let's look at another example. Determine symmetry for y equals x squared plus x. So let's test for y-axis symmetry first. So in order to test for y-axis symmetry, remember we go from x comma y to negative x comma y. So in testing for y-axis symmetry, we replace x with negative x. Okay. In doing so, we're going to take our equation, y equals x squared plus x. We're going to replace the x's with negative x, and we're going to simplify. So again, we know that this is negative x times negative x, which is going to give us x squared. And then it says to add the negative x. One way you can do it is literally subtract the negative, or you can write it as plus negative x. But either way, we started here and we ended here. So when we analyze these equations, we see that there is a subtle difference. This is not the original equation that we started with. The original equation that we started with was y equals x squared plus x. Therefore, there is no y-axis of symmetry. So no y-axis of symmetry exists for this particular equation. Now let's test this equation to determine if there is an origin symmetry. And remember, for the origin symmetry, we go from xy to negative x, negative y. So our original equation is y equals x squared plus x. And we're going to substitute the values that we need to. So y becomes negative y. The x's become negative x. After computing, we have negative y equals x squared minus x. Now, earlier, we had to do one extra step here in example 3 by multiplying both sides by negative 1 to get rid of the negative y as a function, because we cannot leave y as a negative. So we're going to do the same thing here. We're going to multiply both sides by negative 1. When we multiply both sides by negative 1, we're using the distributive property over here. We're going to end up with a positive y. Negative 1 times x squared is going to give us, or excuse me, that should be a negative. In multiplying both sides by negative 1, we end up with, remember, this is going to be a positive x squared. So a positive x squared times a negative 1 is going to give us a negative x squared. And the negative 1 times the negative x is going to give us a positive x. So notice we started here and we ended here. So after assessing these two equations, again, this equation is not the original equation. Therefore, there is no y-axis of symmetry, and there's no origin either. So no y-axis and no origin symmetry either. Now, let's look at another example. Example number 5. Now let's look at an equation that has more than one type of symmetry. Determine the symmetry of x squared plus y squared equals 25. First, we want to test for y-axis of symmetry. So in testing for y-axis of symmetry, we replace x with negative x. Negative x squared, we know, becomes x squared plus y squared equals 25. So notice the equation is unchanged. So it has y-axis of symmetry. Now let's test for x-axis. In testing for x-axis, we have to replace the y with a negative y. In doing so, after computing, we realize that this also has x-axis of symmetry. And then finally, let's test for the origin. In testing for the origin, we have to switch both negative x squared, negative y squared equals 25, which results in x squared plus y squared equals 25. So notice it tends back to the original equation. So this equation follows the test or completes the test for y-axis of symmetry, x-axis of symmetry, and even the origin test of symmetry. So therefore, x-axis of symmetry, y-axis of symmetry, origin symmetry is all legitimate. And so this is important because a graph can have more than one type of symmetry, as we see here. Now, a common error is, suppose if a student says, let's just say, a student is testing, uh, let's use the equation that we had earlier. They're testing y equals x cubed. So, and they're testing for the origin. Let's just say test equation for the origin. So what they do is they say, okay, well, y equals negative x cubed, and they go on and on and on and solve it. Now, if they write this, is this true if they're testing for the origin? What is missing? For the origin symmetry, we must replace both variables. So they replaced the x, but they did not replace the y. So the correct thing to do is to replace y and x. Okay, so this is a common error. All right, so be careful. If you're testing for the origin, you have to do both and not just one. So the correct substitution would look like this. The incorrect substitution would look like this. So remember, again, for y-axis symmetry, change x. For the x-axis symmetry, change y. And for the origin symmetry, change both. Then simplify completely and compare the result with the original equation. So just to review, when you're testing for the origin, or excuse me, when you're testing for the y-axis, you go from positive x, positive y to negative x, y. When you're testing for x-axis, you replace y with negative y, where you're going from the positives to the negative y here. And when you're testing from the origin, you go from, you replace both. You go from positive xy to negative x, negative y. Okay. So if the equation simplifies back to the original equation, the graph has that symmetry. If it goes back to the original equation, it has that symmetry. Same here. So we started at y equals x squared plus 4. We ended at y equals x squared plus 4. Notice we started here, x equals negative y minus 1. We ended at x equals y squared minus 1. And again, it's x equals y squared minus 1 to x equals y squared minus 1. Moreover, in some cases, you have additional steps. So we ended at negative y, excuse me, we almost ended at negative y equals negative x cubed, but you cannot have a negative y, so you have to multiply both sides by negative 1. And then that resulted in y equals x cubed. Notice we started here, we ended here, and we found out that it had symmetry with respect to the origin. And then here, we started at y equals x squared plus x. We ended at y equals x squared minus x. And so we found out that it had no y-axis of symmetry. Now, that pretty much concludes this video. In the next video, we will combine equations, intercepts, and symmetry in a more complete graph analysis problem. Again, thank you for watching.